Today's topic is response surface methods, and we are going to start out with a brief introduction to response surface methodology and talk mainly about the central composite designs today. And we will use a special case study called a whey protein case study to illustrate both the central composite design, some alterations you can make to it, and also to introduce the response surface optimization to you. I assume that most of you have at least done some factorial design work with the two-level factorial designs, and know that those are usually used as a range finding, screening type of design. And we move into the response surface designs when we want to get fine-tuning. We want to find an actual optimum in our process. So response surface methods require more subject matter knowledge than the two-level factorials. Two-level factorials, you can kind of be exploring, which factors are significant in the process, while response surface methods explore how are these particular factors significant in the process. Do they follow a linear function, or do they have some quadratic effects, or perhaps even cubic effects? So we are at the stage where we are certain that these factors do have some significance. We're just trying to more carefully characterize the exact response surface so that we know how to operate our product or process. The goal is to fit the correct empirical model, not so much to detect effects. And we still use the method of analysis of variance to do this. We focus on using contour plots rather than interaction graphs as our method of exploring the design space, since the contour plots can show us a lot of shapes. And then we have to use optimization to find that sweet spot, especially as we get into multiple responses. So as this graphic shows, we are using factorial designs to wander around our region of operability. And then once we feel like we're kind of in the zone, so to speak, then we use response surface methods to fine-tune and find that exact sweet spot where we can make the product the best and the cheapest, and however we meet our goals for quality characteristics. This is kind of maybe a little intimidating graphic at first. Lots of Greek letters on here. This is just illustrating the type of polynomial function that we can fit using response surface methods, starting with an intercept and going into our linear terms, and then going into our second degree terms. So we have first degree terms, which are linear, and second degree terms, which are both the quadratic terms and the two-factor interaction terms. Then we proceed into the cubic terms, which most people think of as like a cubed or b cubed, but we can't forget those extra terms that look kind of strange, like a squared b or ab squared. Those are also other cubic terms that describe other types of shapes in our polynomial. As most processes can be fit with quadratic polynomials, it's rather rare to go above those. If we do need more than quadratic, then often we want to just do a double check and make sure that we don't need a transformation, or we have any outliers in the design space that are messing up our polynomial. We might need to restrict the region of interest so that we can get a better fit in a smaller region. And if none of those are needed, then certainly using a higher order polynomial can also accomplish the task. I have a few slides here that show the types of shapes that we might be able to fit with a quadratic polynomial, starting with the simple maximum, or if you flip this upside down, you can get a minimum. Then there's a rising ridge, and we can also have stationary ridges. Finally, the golden grail, the really cool shape, is this saddle, or MiniMax, as it's called. This is actually a fairly complex shape, and the complexity is great. It allows us to model a lot of different types of functions. So, I mean, a quadratic polynomial maybe seems rather plain, but it's amazing what it can describe as far as the shape of our response surface. So because of this, quadratics are often all that we need as long as we have restricted our design space to a fairly narrow region. Usually response surface methods use a quantitative response, which means some sort of numeric response, and it's affected by these numeric factors, continuous factors. It usually works best when we've gotten down to just a handful of the critical factors, the ones that survive our factorial design screening stages. We're focusing again on our polynomial model, developing the best model that approximates our response surface. And our focus becomes optimization. I've done a lot of work with contour plots in my previous life as a process engineer, and so these contour maps are wonderful for describing the surface, describing the area in which we can have our best operating conditions. And so response surface methods, this is really what they're used for. Okay, now what are my favorite designs? Favorites are above all else the central composite design. Yeah, it's a classic design. It is in textbooks all over the place. It's 5 levels. Every factor is set to 5 separate levels, and it really has great statistical properties. Now, I have certainly been in situations where setting some of the factors to 5 levels was just too extreme, and so the Box-Benken design is another great alternative that's only a 3-level design. It also has very good statistical properties. Usually it has a couple fewer runs, which can be a bonus. And finally, my third choice is certainly the optimal design, or custom design. The optimal design is customizable for nearly any situation. It can handle constrained design spaces, it can handle categoric factors, and just quite a variety of circumstances. So when you look at your design space, we'll see some pictures here in a minute. If a central composite design can adequately fit your needs as an experimenter, then I would absolutely recommend it. If you need to customize your design space, then going to the optimal design is also an excellent option. So because this is our part 1 of this 2-part series, we're going to focus today on the central composite designs and just the basics of what you can do with them. So here's a picture of our central composite design. And you can see the blue balls are the corners of the factorial design space. And you have the red dot in the middle, that's your center point. And then, of course, the exterior points are the star points or axial points. Now, one of the things that you want to understand about this design is that the best predictions are within those blue balls, within the factorial space. We use the outer star points as a way of getting very good estimates of our quadratic terms, but we're never actually meant to make good predictions out there. If you notice, we only do a single run out there. So I don't know about you, but I don't care to to invest a lot of time and energy into an area of the design space where I only have made a single run. So these are good supporting runs, but you have to remember that your best predictions are within the factorial space. And the defaults of the model graphs, if you've been using Design Experts at all, the defaults of the model graphs are the ranges are the factorial space, the plus and minus ones, and I know you sometimes ask questions about that, but that's because that's where the best predictions can be. So those factorial points are used to estimate your main effects and your two-factor interactions. Your center points are used to tie blocks together, especially if you've had to run central composite in multiple blocks. Then we have a common link between the different blocks. And also to provide an estimate of the pure error of the process. And so, of course, those center points should be randomly distributed throughout your runs, so that you maybe do some towards the beginning of the experiment and then some later on in the experiment. These star points are used to estimate our quadratic effects. And so when you tie all these things together, we can estimate actually polynomials from a linear polynomial to a two-factor interaction polynomial to a quadratic polynomial. So it's a very flexible design. Remembering that when we have multiple responses, each response is not going to be modeled the same. One response might need that quadratic, but another might only need a linear. So the central composite design functions well for optimizing, for being able to fit all of those models. Okay. So here's a little breakdown of the types of runs that you're going to use. The factorial points are ones that we're probably used to. To me as an engineer, working when I first started with these back in the early 90s, the fascinating part to me was the axial runs. These axial points or star points are stretching out from the midpoint of the design space. And if you think of it, this is kind of like what you might do in a one factor at a time experiment. You set all your factors at a specific level, and you change one factor to its extreme, to another level. So taking that first axial or star point, you've got B and C set to its center point, and A stretches first really low, and in the next run it stretches really high. So you can kind of imagine that as being a one factor at a time test, almost a range finding test. And then you go to the next set, the next pair of runs, which keeps A and C fixed and stretches B to its low and high level. And the same with C in that last little block. Now, all of these runs in a complete central composite design would be randomized, all mixed up, jumbled up together. So I'm not suggesting that you run these in this order, but I just wanted to kind of point out that there is a sense of that one factor at a time testing built into this central composite design that I think is rather neat. And to be honest, that relationship was just pointed out to me last week while I was attending the Fall Technical Conference down in Kansas City, Missouri. It was quite an interesting talk by another consulting statistician. So we can learn new points of view all the time, even if we've been doing this for a lot of years. Those center points, just to comment about those also, the center points are really critical that we also randomize those amongst the factorial and axial points so that we get a good feel, a good estimate of the random process variation in our experiment. If you run all of your center points together, then what's going to happen? Now think about it. How much variation is there from one point to the next if you've just run them all back to back? Then you're down to sample variation and not random process variation. So in order to do all of our tests correctly, we need to run those center points also correctly. So this is just one more graphic to remind you that we need to keep those axial or star points within the region of operability. They can be outside the region of interest, but they need to be within the region of operability. We make predictions in the region of interest. Now, what happens when those star points are kind of nosing out, and you set up your central composite, and it tells you, hey, you have a axial run that's all of a sudden negative. It's like a negative time or a negative temperature. That doesn't make sense. Well, actually, in Minnesota, we have a lot of negative temperatures, so I guess that would be okay. But we certainly don't want negative times. So we will comment on that in this next case study that we're coming up on next. All right, so we're going to get into this whey protein concentrates case study, and shortly I will bring up Design Expert, and I will be switching from these PowerPoint slides into the software. So the unique part about this particular case study is that the ranges here are noted not as your -1 and +1 levels, but they're actually the exterior ranges for each of these factors. They are listed as the alpha or star levels. So the heating temperature, our limitation is 65 to 85, and our pH level is 4 to 8. The redox potential can go negative, that's okay. And the other two, the sodiums, are limited. Their lower level has to be 0. We can't go below 0 on these. So we have 5 factors. A 2 to the 5th factorial design would be 32 runs, and then we add the axial points to that and the center points. But that 32 run base is an awful lot, is pretty big. So these experimenters chose to do a central composite based on a 1/2 fraction. So they're going to use a 2 to the 5 minus 1 as their base, and then augment that with the axial points and the center points. And they're going to put in the alpha levels rather than ±1 levels. So I'm going to show you how to do that here on these next screens. So afterwards, you can certainly go back, open up your Design Expert and follow these instructions. So you choose a 5-factor design, and then you choose a 1/2 fraction of that design, and then you click on the Enter Factor Ranges in terms of alpha. And this should give you a design that has a total of 32 runs. Now, you don't need to do this, but if you were to click on the Options button, you would see that the rotatable alpha is 2, so we're going to have ±1s and ±2s. There's a lot of options for your alpha that we don't have time to get into today. We certainly go through all these things when we do our workshops, but in a 1-hour presentation I don't have time to cover all these. Let me just point out that there is an option here for a face-centered. It says alpha of 1.0. That is a fabulous way of making a central composite design into a 3-level design. So feel free to use that, especially if you have, just a reasonable number of factors, 4 or 5 factors. Once you're above 5 factors, then the default alpha value will be about 1.5 or so. We switch to what's called a practical alpha value. So these are the positioning of these star points, these axial points. Okay, so we're going to enter these factor ranges as their alpha values, and you can see on the screen that if I enter 65 and 85 as my ranges, that my -1 and +1 levels are 70 and 80. And for my pH, if I enter 4 and 8 as my minus alpha and plus alpha, I'll get 5 and 7 as my -1, +1 levels, etc. So, you know, if you know the bounds of your space, you know you don't want to exceed those, then this is just a great alternative for you. Okay, the next couple pages are the data for this design, so I'm not going to spend any time on these, but it's here for you. If you want to recreate this design, you're certainly welcome to. We're actually going to look at, I have analysis of 3 responses here. We're going to look at undenatured protein and whipping time and the time at first drop from this particular journal study. So bear with me a moment while I launch my Design Expert. You see Design Expert now? Okay, so I have Design Expert now up on the screen. I have this design with the 5 factors in here, the 3 responses. And we're going to walk through the analysis of this data. So I'm going to click on my undenatured protein, and I'm going to go straight to the Fit Summary button. Like I said, in the interest of time, I don't have time to go in depth into all these things, but my goal here as kind of a basics overview of response surface methods is to hopefully just teach you just enough so you can do a basic analysis of a response surface design. And we do have tutorials available to show you, to walk through this again, where you can read through all the instructions on how to analyze a response surface design. So those are available on our website. If you want information about those sent to you, we can certainly send you the links directly. Just send me an email afterwards and I'd be happy to do so. So in Design Expert version 8, we've put a summary screen right at the top. The detailed tables are below here. There are 3 tables, but I love this summary screen because that's pretty much all I look at now. In this, we first of all look at the p-values for each of the models that we're attempting to fit. So the p-value of the linear model is less than 0.05. So that tells me that those linear terms do have a significant fit. And that's a good thing. That's what we're looking for. The second column, however, is a column called our lack of fit column. And lack of fit is, it's a great double negative. You want your model to fit. And so the lack of fit measurement is something that if lack of fit is significant, then your model does not fit. And so that's a bad thing. So whereas the first p-value says, hey, these linear terms show some significance, that's good, because lack of fit is also significant, that means the model is not fitting in the whole design space. Something is not being explained yet. So that's a bad thing. Then the next 2 columns are the adjusted and predicted R-squared values. And they range, well, in general you can think of them as ranging from 0 to 1, with 0 being low and 1 being high. That predicted R-squared can actually go into some other numbers, as you can see by the line below. It can even go negative. But those are some idiosyncrasies with it. In general, higher is better. So, 0.5s, that's just kind of a moderate fit. This adjusted R-squared tells you the amount of variation in the data that's explained by the model. Let me repeat that. It's the amount of variation in this data that's explained by the model. So this model is explaining about 58% of the variation. Then our predicted R-squared is telling us the amount of variation in predictions that's explained by this model. And so that's about 46% roughly. Okay, so let's compare that to the next model down the line, the two-factor interaction. That's what 2FI means, two-factor interaction model. Now, what we're doing is we're simply testing the addition of these terms. And the addition of the two-factor interaction terms to the linear terms doesn't add anything new. It doesn't add anything of value. So although we have some linear fit, we don't really have much for interaction fit. And again, the lack of fit is it is significant, which is not good. So I'm going to kind of skip that one and go down to the quadratic. The quadratic model is significant. The lack of fit is 0.04, which is just borderline significant. So, it's not perfect here. Maybe we'll have to see what's going on. The adjusted R-squared is 0.89. I mean, you can always almost round that to a 0.9. Very, very good. But the predicted R-squared is 0.16, so that's actually quite low. However, of our choices, this quadratic model is the best model, and it is the one that the software has a statistical magic thing going on inside of it, and it does suggest this as the best model so far at this stage. The next model in line, the cubic model, is aliased. So that's not good. That means that we cannot actually estimate all the cubic terms. Remember that list of terms? You have not only a cubed and b cubed and c cubed and d cubed and e cubed, but you have all those cubic combinations of those things. So there's a lot of cubic terms to be estimated, and we can't do that with just a central composite design. So we're going to stick with the quadratic model, and we'll see if we can't improve this predicted R-squared. Okay, so what I'm going to do next is click on the model button, and you can see right now on this screen that I have the quadratic model selected, and I have all the terms for the main effects, all the two-factor interactions, and all the squared terms put in the model. That's what the M's mean. What I'm going to do is I'm going to do some automatic model reduction. So on the selection button, I am going to click on backwards model reduction. This is going to remove for us all the terms that have p-values that are greater than 0.1. You see this alpha out value? If the p-value is greater than 0.1, then the terms will be taken out for us automatically. At the end of taking out those terms, we'll also get a little question asking us about hierarchy, and so we'll say yes to that. We'll see if that pops up here. So I'm going to click on the ANOVA and let this run. There we go. I have the warning that the model is not hierarchical, and anytime you get this warning, just say yes. This means that we want to add back in the main effects that are needed to support any higher order terms. Okay, so I said yes to that button, and we get to our ANOVA screen. Since we've done backward reduction, we get a little table that tells us what terms have been removed, and you can see we removed about 10 or so terms. There's quite a number of them. And we added back in a couple of them needed for hierarchy. So this is still, with my reduced quadratic model, I still have a significant p-value, and I have terms that are quite significant. And I'm just scrolling down a little bit. I want to point out, once we've done that model reduction, we're taking those insignificant effects and we're putting them into the error where they belong. And so only significant effects remain in the model. That improves your predicted R-squared tremendously. We went from a 0.16 all the way up to a 0.85. So just that's like a little magic trick, statistical magic trick. So backward model reduction, when you have a fairly substantial group of terms that's not significant, then you definitely want to get rid of them, put them into the error pool, and that will bring your predicted R-squared up very nicely. Also, the adjusted R-squared has also gone up a bit too. So now they are within, our recommendation is that adjusted R-squared and predicted R-squared should be within 0.2 of each other. That's just a guideline, be within 0.2. And they are now. So I would consider this a pretty good fitting model. The lack of fit is also now at a 0.1297. So lack of fit has also gone not significant, and that is also a good sign that we've done a decent job of fitting this. You know, are we ever going to get perfect? No. We work in the real world, and to get perfect models, you need to go back to those college textbooks. So we often just have to do the best we can. Okay. Now, the next step would be to look at your diagnostic plots for this ANOVA. And I'll run through some of the basic plots here. The first plot is your normal plot of residuals. And this is a test to make sure that our residuals are normally distributed. And we are looking to find these points falling on pretty much a straight line. Now you have to know this is like the flakiest graph of all the diagnostics, so you have to be willing to give it a little bit of leeway. I've seen plenty of waviness on things that are still normally distributed, so this one's absolutely fine. It's straight enough. The nice thing to know is that the ANOVA test is insensitive to even moderate deviations from normality. So you don't have to get all that hung up about normality. It's it's still something that's important, but the ANOVA is not all that sensitive to it. And you'll find this statement in those college textbooks that we're insensitive to even moderate deviations from normality. So that's reassuring considering the amount of stray that you'll see on this graph. Okay, I'm going to click on the second one now, which is the residuals versus predicted values. And this is where we're looking for constant variance. We're looking to make sure that these residuals are at about the same, have about the same up and down spread from the left side of the graph to the right side of the graph. So if you look at the x-axis, your predicted values are 30 to 90. So we're talking about predicting small numbers versus predicting large numbers. We want the variation in those predictions to be about the same. Sometimes what happens is as you predict bigger and bigger numbers, the variation gets bigger. And as you predict smaller numbers, the variation gets smaller. That would result in what's called a megaphone effect, or kind of that horn, a bell shape, a horn shape expansion from the left side to the right side. And that would be a violation of one of the assumptions of the ANOVA, that you have constant variance. If you do see that, then that's a clue that you might need a transformation. The next graph we're going to look at is simply the residuals versus run. Now, this is probably one of the most important graphs that you should look at in your own designed experiments. This is where you can possibly see trends, see things going on. This should reflect the time order of your experiment. And ideally, it's just a random process variation. Now, the fact that the 4 dots are kind of all together at the right side, on the right end of this graph, would definitely cause me to go back to those 4 and just check them out and make sure that they were all, that say they weren't all center points or something like that. I'd want to make sure that that was good data and still representative of the process. Okay, so just watch for any abnormalities on that graph. Another graph, I'm going to skip a couple here, but I'm going to go down to the Box-Cox plot. And this is certainly another plot that you should look without even understanding this graph. All you really need to do is look on the legend on the left where it says recommended transformation. It says none right now. That means that no transformation is needed to analyze this, and that's really all you need to know. If it was recommending something, it would say log or square root or something like that. If it did say that, then you could go back to the transformation button and apply that, click on it, apply that, and reanalyze. So it's just a very fast way of picking up on the need for a transformation. That came into existence maybe, or into the software maybe 10 years ago or so, and it's been fabulous. Before then, we had to literally run every single transformation option and just look at the ANOVA values and try to figure out which one looked better. The last graphic that I always look at is over on the Influence tab on the Diagnostics tool that's on my left side. I'm going to click on the Influence button, and I have my externally studentized residuals, which is a scary, scary name for a really simple concept. This is your outlier graph. This is simply your graph where you look to see if any of your data points are outside the red lines, and if so, they would be considered outliers to this model. Now, that doesn't mean they're bad data points. It just means that you have a discrepancy between that point and the model. Either the point is wrong or the model is wrong, and that's where your investigations should start. You can look into that. Okay, so that was a brief run-through of the diagnostics. If you want kind of instant help on the diagnostics, you can always click on the little light bulb that's at the top, and you can get little instant help popping up on your screen. Okay, so finally, I'll just click on the model graphs briefly. This is our pretty picture of this undenatured protein. We haven't even gotten to the goals of this yet, but we'll get there shortly. I want to be able to optimize this in total, so I'm actually going to quite quickly analyze the other 2 responses, so then we can add all 3 of these into the numerical optimization in our remaining 15 minutes here. So I'm going to click on whip time and click on the fit summary. See, and this is just a great little example. Look, in this particular case, we have 2 suggested models. What do we do now? What's going on? You can see the linear model is significant, but it has significant lack of fit. And the adjusted and predicted R-squareds aren't really very good. 0.1, 0.3, not numbers that I would prefer to have if I'm trying to optimize my process. The quadratic model is also significant, and it also has significant lack of fit, although not as much. The adjusted R-squared is a fair amount better, but the predicted R-squared is worse. It's -1. So what do you do in a situation like this? Well, the best thing to do is to proceed with the higher order model. So the quadratic model is a higher order model. We're going to proceed with that, and we're going to do some backward reduction out of it and see where we land after we get rid of the terms that aren't needed. So I'm going to click on Model. I'm going to go ahead with the backward model reduction again. I'm going to click on the ANOVA. Oh, say yes to hierarchy. And look at, wow, I must have taken out about 13 or so terms. Took out a lot of terms. Until I'm left with a model that does fit well. You know what? My lack of fit is still just a little bit off, 0.03. You know, and this is one of the situations, I know this data set, we're really not going to get much better with this. You know, could we take out the DE? That's your choice. You can if you want to. We're just not going to get a whole lot better. This is still a pretty decently fitting thing. Our R-squareds, at least, are positive. Adjusted R-squared is 0.8, and predicted R-squared is about 0.6. So they are within 0.2 of each other if you just round a tiny little bit. Let's check diagnostics to see if there's any problems. But if there's no problems in diagnostics, then we're just going to go for it. And you can look at the graphics and check out, you know, see if you can figure out reasons for that lack of fit. But I'm not going to do that here. So our normal plot of residuals looks pretty straight. Residuals versus predicted. I don't see any big megaphone effects, so I think we're okay. Residuals versus run is just pretty much random scatter. Oh, here we go. The Box-Cox plot recommends a log transformation. So we should do that. So we're going to go back to the transform button, and we're going to put on, I generally use a base 10 log. You're welcome to use a natural log. They both do pretty much the same thing to the data. My fit summary still shows 2 suggested models, so I'm going to redo this analysis. I'm going to do the same thing, quadratic, with the backward model reduction put on it. Yes to hierarchy, and we'll see where we get. See if we improve anything. So here we are. We have a model p-value that is significant. That's good. And we now have no lack of fit. So that is a success. The predicted and the adjusted and predicted R-squared values are, actually they're very similar to what they were before. We had a 0.8 and a 0.6. Now we have a 0.78 and a 0.65. So they came together just a little bit, but they are basically about what they were before. You have to check diagnostics one more time. And don't forget to do that. Now this normal plot of residuals is straighter than it was before, so that's always nice if you see a little improvement. Residuals versus predicted didn't really change much, but it wasn't bad before, so it's fine. I'm going to return one more time to the Box-Cox plot. And, it says I could adjust one more time. I'm not going to do that in the interest of time today. You can see how that there are 2 transformations that are very similar to each other. The inverse square root versus the log They're very, very similar to each other. We're not going to get much additional gain, so if I had the time, I'd probably go ahead and throw that last one on, but I'm not going to do so here. Okay, so then we end up with the model graphs on the whip time. Let's do the time at first drop. So again, starting with the fit summary, we're going to go with the higher order model, which is the two-factor interaction model. We're going to do the backward model reduction. We're going to say yes to hierarchy. And we're going to check our model statistics. The model is significant. Lack of fit is pretty severe in this case. And there is a difference between the adjusted and predicted R-squareds. Look at that, 0.64 and 0.34. So this becomes a decision point. There's nothing more in the diagnostics. I've looked at this. There's nothing more in the diagnostics that we can really do. It turns out with this problem that we do have some problems with these axial points, that perhaps they were set out just maybe a little bit too far, and we are having some problems fitting those axial points well. If you look into this problem, you actually fit the center of the design space quite well within the factorial cube, which is what we want. But when you expand out of that, that's where we get the strong lack of fit. So because I've been able to investigate this outside of this webinar, I'm going to choose to continue on with this model and use it in optimization. But that's a decision that you guys have to make as you're going through your data analysis. And I mean, isn't this the real world? I had, the first response analyzed great. The second one was pretty good, and this one is just not perfect. But by looking through it, I can, understand that the lack of fit is at the edges, and which is not where my likely optimum is, and so I can still choose to use it. When you email or call us and ask us those questions, you say, can I still use this model? We're going to turn that question right back to you and say, that's a subject matter knowledge decision to make. From a statistical standpoint, we can't really make that decision for you. You have to decide if it will still work and meet your business needs. Okay, so now we're going to go into numerical optimization. And we're going to go down to our undenatured protein, which we want to maximize. So I'm going to put a maximum on that. And, although we physically measured an undenatured protein value of 36, that is absolutely pitiful, and there's no way I could ever accept that number. So I'm thinking more about my specifications now and say, you know what, my minimum spec is an 80. I cannot have anything less than an 80, and I would really like a 90. So I'm going to set my limits to be 80 to 90 because that's where I want to go. I want to maximize this. Above 90 would be great. This is my most important response, so I'm going to make this a 5-star response. And that's what importance does, just says that, hey, this response is more important than another one. The whip time is my second one. This is actually the least important response, and we want to minimize it. So I'm going to put this down to a 2-star. And as long as this is below 4, this value of 4, if I'm below 4, I'm fine. Lower is better, and a 2 would be great. And finally, my time. I want to maximize the time. And the minimum time is going to be 10 to 36. And we'll leave this at 3-star, kind of a moderate importance. So then we click on our Solutions button, and we get this table. Now this table lists a range of solutions. I get a lot of solutions. And, you know, why doesn't it list just one solution? Well, do you really want just one solution? Preferably, we get a long list of solutions. It tells us we have multiple ways to operate our process that are all good. Now, when you look at this list of solutions, you'll see that, you know, all these top heating times are 70. The redox potential is all between 0.15 and 0.18, so it's very, very similar. The sodium oxalate is all 0.03s. So you can see a lot of similarities. The differences occur in, you know, there's just a slight more range in the pHs. So, you know, the whole process isn't very dependent on pH. But we can definitely get a number of solutions that meet our needs. Now there's kind of a cool little picture here. I don't know if you've used it very much, but it's called the ramps view. So I went over to the left to my Solutions tool, and I'm going to click on ramps, and you can see just visually for each factor you've got the low and the high settings, and so my heating time has got to be low. The pH, you know, kind of right in the middle. The sodium oxalate, a little bit more on the right side, the higher end. The sodium lauryl is definitely on the high end. The redox potential is right smack in the middle. And then you can see for that solution how closely we met our goals. The undenatured protein, well, we at least got partially up the ramp between 80 and 90. The whipping time we got below 4. And the time at first drop we got, you know, just above 10. And that's, you know, that's about the best we can do with these models. So we met all of our goals. You know, maybe didn't, you know, totally maximize or minimize these things, but that often happens when you have multiple responses that have kind of competing goals. The fun part about this is that once you have these models, workable models, then you can you can go back and change the criteria, modify the criteria. If you have any factor, you know, maybe is expensive, you can work to use less of it or a less expensive setting. So you can start playing and modifying the criteria and hone in on a variety of options. And then you can go out and do some confirmation runs at the end. That's the very next step. So I would take the solution that's found here and go out and do some confirmations. And you can put that into our confirmation node. This is a pretty new tool. If you don't have version 8.0.6, you might want to download the free update to that version and make sure that you have this confirmation node. I can tell this node that, hey, I'm going to go do 5 confirmation runs. And with the 5 confirmation runs, it's going to tell me a 95% prediction interval in which we need these runs to be in. So as long as my runs are within those, we should be good to go. Okay, I'm going to flip back to my PowerPoint. Excuse me while I have to do a real quick flip through because my controls aren't all working here. Okay, so just to summarize our response surface designs here. When we're doing response surface methods, our goal is optimization. That's why we're using response surface methods. The central composite tool design is a fabulous tool when it fits the problem. And so that's what we've been illustrating here. The optimal custom design is fabulous when it's needed. So that's going to be part 2 of our series of webinars here, and we're planning to do that in December. We haven't gotten that scheduled yet. And numerical optimization is obviously a key part of the optimization process. Now I'm just noting that somebody did put in a question that I think is probably on everybody's mind. It says, in this example, should the design space for temperature and the sodium lauryl be reevaluated? Absolutely. Yeah, that is definitely, they didn't quite hit. They put in these plus or minus alpha values, but, just maybe weren't quite correct. And yeah, so reevaluated would be the correct way of saying it, versus, they screwed up. No, they didn't screw up. Remember, this design actually had 9 responses, and so I think for some of the responses, those ranges were appropriate, but for other responses, it was just kind of an overextension, and they went out a little bit too far. It goes back to that original slide that said, hey, if you need a higher order model, perhaps you need to reduce the design space, and I think that's what they hit in this particular case. If you want some other great explanations of response surface designs, the Response Surface RSM Simplified book is a great option for you. It's available on our website, and it's just past 11:30 now, so I am going to wrap up this webinar. I think Brooks has been taking care of questions, and I want to thank him very, very much for doing that on the fly. If you have additional questions, I would welcome you to email me, Shari@Statties.com. I would be happy to answer those, and I can even send you the data file if you are interested in getting that. And I can check and see if we can post that up on our website also. So as it says, best of luck for your future experimenting, and thank you very much for listening. See you in December for our next one.